Alrighty. Just to keep the show going, thank you so much for your attention and the invitation. Really loving my time here in Vietnam. First time I've been here, and I'm really excited to have the chance to visit and just interact with you all and find out about sort of the economic miracle that's going on here in Vietnam. So my talk today is on the rise of neural priors, which sounds like a bad HBO series. So I've decided to sort of slightly augment the title and basically simplify it down. Learning with less, okay? So, and one of the motivations, right, is that if you're following a lot of social media or you're a bit of an AI fanboy or fangirl, just following what's going on, the thing that we're really noticing, right, is this whole trend around emergence in AI. Right? So what do we mean by emergence? So one way to think about emergence, right, is I've got a graph here. And so on the x-axis, I've got the amount of training data. Right? So it could be text, it could be vision, it could be any modality you're thinking of. And on the y-axis, you've got performance. And so the general paradigm in AI and deep learning, probably since sort of the last decade or two, has essentially been this. Right? So we add more and more data, all right? And this is on the log scale. This is not linear. And I start getting more and more performance, okay? So in many ways, right, it's almost like baking a cake. We've kind of got the recipe. We've seen the revolution of LLMs and transformer networks. And there's this view, now we're not sure whether it's a correct view or a mistaken view, that the real challenge now is just scaling. How do I scale this up? How do I throw enough compute? How do I throw enough data at it? Okay. So, and we're seeing lots of amazing results in industry coming out because of the scaling, because of emergence. Now, there's also a great, if you guys haven't read it, there's a great article by Rich Sutton on the bitter lesson that sort of talks to this about sort of really data and scaling is sort of at the heart of a lot of what's going on. Now, I've had an interesting career. I've been a professor most of my life. Well, I was an adult first, and then I was a professor. But I also worked in the autonomous car industry for a number of years. So for a company actually in Pittsburgh called Argo AI. And I learned a lot through that experience in industry. So autonomous cars are interesting. One of the things that they have to do, right, is in really quick time, they're driving down the street, and I think the ultimate challenge for an autonomous vehicle is to navigate the streets of Ho Chi Minh City. I think that would be the ultimate test in many ways. So, but let's make it an easier task, perhaps something in Pittsburgh, for instance. And so what are we asking of these systems? These systems are sort of ingesting huge amounts of data. So video data, LiDAR data, radar data. And in real time, you've got these deep networks rapidly making predictions, right? So detecting the object, detecting people, forecasting. So Marshall was talking about large elements of this in his talk. And so really difficult problem, right? But the whole thing is, if we get enough data and we get enough compute, we're going to get there. We just need to give it enough, just more and more and more. One thing I think about a bit, and many of you in the audience have probably seen this, Andrej Karpathy had like a great tweet last year. And for those of you who are not AI fanboys or fangirls and perhaps don't read statistics on a Friday night and actually have active social lives, there's an interesting tweet here. The real world data distribution is N01, but a good data set is U -2, 2. All right? So I could be speaking Klingon here, but I'm going to decipher this tweet. So what it really comes down to is this image. It's a difficult image to look at. It's a small child walking out to the street. Fortunately, this child was okay. Nothing happened to this child, right? But you can be driving around in various cities in the world, perhaps for years, and you may never encounter this. Very, very rare. Now, what Andrej's point was that basically this is a tale. This is something very, very rare. It happens very, very rarely. Stop signs, pretty regular, right? We kind of run into them all the time. AIs are reflections of the data that they're ingested. Right? So we have a problem at the moment. And so basically, the current paradigm for AI would work excellently if all events and all things that we care about were equally likely. But unfortunately, the world isn't uniform. It is Gaussian. We have these really, really rare events. And no matter how much data I collect, I could be collecting data for decades, I am still not going to get enough samples to cover all these important examples. So, what to do? And there's a lot of interesting things that can be done, and I'm not going to cover all of them. But one of the motivations is that we need AIs and robots to be going into brand new scenarios that they've never seen before, perhaps underwater trenches deep down in the ocean, perhaps in brand cities where there's perhaps conflict going on. I might not have data for that city. I might have a defense application where I'm trying to get a robot into a brand new scenario, no data, I don't know what I'm going to encounter. Or perhaps I'm trying to detect a rare form of cancer. Very, very few examples of that. How do I handle that type of scenario? Another great example of this is in GPT-4. And I'm sort of shamelessly borrowing this from a CVPR keynote that I saw while I was there by Yen-Jin Choi at University of Washington. She had a great example just saying, even in GPT-4 we're seeing this. So if you ask GPT-4 to multiply two numbers together, it'll give you an answer that looks kind of correct, right? But it's actually wrong. And what's really interesting in her paper, she showed that as you increased the number of digits, so if it's 3-digit by 3-digit, at 59%, 4-digit by 4-digit, 4%, 5-digit by 5-digit, 0. Right? Now, I agree, you could plug in Wolfram or something else to make it do multiplication. But it's also further evidence that neural networks are kind of like errant children. They're always looking for the easy way out. They're always looking for shortcuts. Right? So, and for a lot of problems, we can never give enough data to the system. I can never show it all combinations of multiplication. Right? And so this is not about multiplication. Multiplication is an example of this problem more broadly in transformer networks. Vision, language, anywhere. So, and great paper. If you guys haven't seen it, it's an excellent paper. So, one thing to note, however, is humans don't quite learn like LLMs learn. We are really efficient in our learning, right? So we can get really good performance with small amounts of data. So how do we do that? And so my hand-wavy sort of definition is, one way to do that is something we're calling a neural prior. So what do I mean by neural prior? So neural prior is basically about how can I make a learning system more efficient with less data. So in the work that we've been doing on neural priors, we've been looking at sort of 3 types of directions. One direction is around architecture, so new architectures. So transformers are amazing, but they're perhaps not the be-all and end-all, especially for data-efficient learning. The second thing is optimization. Now, I sort of lament as a professor, I think the current generation of students coming through think about optimization basically as SGD, or perhaps Atom. But there's a whole slew, a whole space of techniques around optimization that we're kind of ignoring. And the other thing that's kind of interesting too is initialization. And this is one that I think most students really, really ignore. It's under the hood. If you're playing with PyTorch or TensorFlow, you design your brand new network, you're training it, you don't typically think about initialization at all. But there's a lot of evidence coming out that it really matters. And so that's a really, really interesting development happening in the field too. So let's talk quickly about architecture. So we're living through this phenomena of self-supervised learning. And in vision, basically self-supervised learning, just like in language, is you have an image, you take parts out, like patches. One thing that's interesting with vision is vision requires a lot more masking than language. So for most vision transformer networks, you need to mask an image at 75% of the signal to get it to work. So, and that's another really interesting question too. How different modalities require different amounts of masking. And so essentially the process works, you ingest an image, you encode, decode, you try to reconstruct the image, and you can train from huge amounts of images to actually recover the signal. Now, one of the problems, however, is that when you do this, your weights, when you deploy the network, are frozen, right? You train it, it might take you a week or a month to train it, but then at runtime, you're not optimizing anything, it's just frozen in time. And your hope is that you've just shown it enough examples, enough variations that whatever it runs into, it will behave well. There's no mechanism for feedback, nothing to sort of take some information from the thing you're trying to predict back to the signal. So one thing I want to kind of flag a little bit is some interesting work that was done by a really well-known professor, Andrea Vidali at Oxford. And he published a paper in 2018. It's pretty well known. It's called Deep Image Prior. And this is sort of where we're borrowing the term a little bit from. But it's a really, really crazy idea. Imagine, but I love it because I love when I teach my classes, oftentimes they don't have a lot of compute. They don't have a big GPU to play on. So this is a great experiment to run because you can run this with a single image, one image. So you get the image, it's perhaps corrupted, perhaps a patch or something missing, and you have a random code. The code can just be random, so you have Z here. And all you're doing, you're trying to reconstruct the image with the neural network with that random code, just on the one image, right? And so what you can do then, what's really nice is when you do the optimization, there's a feedback going on, right? It's kind of sending information back through the system. And what you can do then, and what was really, really amazing with this work, is that when you actually train this network and then try to reconstruct the signal, you can recover the missing information. Now, many of you guys, oh, big deal, neural networks can do that. This has not been exposed to any training data. So how does it know to fill what's in there, filling back that missing information? And so what Andrea was sort of arguing is that the network architecture itself has information. So the architecture, not just the data, gives you a bias, can give extra information, and perhaps holds the key to making learning much more efficient. So we actually see modern versions of this now. So many people, and Marshall spoke about something that's very common in computer vision now, something called neural radiance fields, NeRF. So NeRF is essentially this idea. So NeRF takes a single image, or can work with a single image, or just a few images, say 10, 12 images, and instead of having a random code, it now feeds in coordinates, but they're just still fixed. And you train a neural network at runtime. It's not trained on billions of images offline, just at runtime. And again, and they call these things coordinate networks because the positions are simply just X and Y in the signal. You can do this in a time series. You can actually do these in high dimensional fields. And you just essentially try to recover the RGB value. And so this is made very, very famous now by the NeRF paper back in ECCV 2020. And if you go to a CVPR conference, you oftentimes run into people wearing NeRF t-shirts. It's a big, big thing. And there's this whole field now emerging around representing signals as neural networks. Right? So largely when we deal with neural networks, we use them to transform a signal. I'm doing some sort of segmentation, I'm predicting something. Here, you're trying to represent the signal as a neural network. Right? So it's almost like neural signal processing. And it's really, really moving quickly at the moment. And so the whole idea is that you have some coordinates, so X and Y. You feed that into a neural network, and it essentially just predicts the image. And so what's really awesome with this, again, is that if you're a student, you can actually train a neural network up on one image. So in some of the classes I teach, we actually have a competition. Who can come up with the most creative architecture to reconstruct the signal with the most degradation, just using their architecture. So it trains on coordinates. It reconstructs, not transforms the signal. And people oftentimes refer to these things now as implicit neural functions, or more commonly, just something called a coordinate network. All right? Now, the most useful application for this at the moment is modeling radiance fields. And for those of you who don't know what a radiance field is, I'm not going to go into it, but essentially it's a 5-dimensional field. So you can think of it as a function that takes 5 dimensions going in, essentially X, Y, and Z, and viewpoint. And what you can do is if you have that radiance field, you can basically recast an image from any viewpoint. So if you capture the radiance field of the scene, I can actually reconstruct the image from any viewpoint. And so really, really useful property. So you can do things like being able to reconstruct your favorite Christmas tree. But a really cool application was something done by Waymo recently, something called block nerf, where they applied this to all of San Francisco. So they nerfed the entire city. Now, why? Well, this goes back to Andre's tweet, right? It's like data-driven simulation. You're actually using the data to drive the simulation. So if there's an area of the street or an area that you didn't quite go down, you can actually resim it down. And so a lot of companies are investing big in this direction, right? So this is one way to get around the towel problem, to do data-driven simulation. So NERF is really at the leading edge of this. And there's extensions now like Gaussian splatting and other things to do things faster, but this is a really exciting emerging field. So one thing we noticed, but it's also really interesting about coordinate networks, is coordinate networks essentially they have a spectral bias. So if you're playing with a coordinate network and you take your traditional network like ReLU, like the ReLU network, we all get taught about ReLU, and this is this sort of thing here that I've put here. If I feed a coordinate network and run it through, say, a 3-layer or 4-layer ReLU network, I go and train it, I don't get a great result. I can train it for a while, I can train and train and train and train, but it's really hard to make out what this image is, right? And this speaks to what I find fascinating with this. It also shows where current techniques in deep learning break, right? So the activations that we use for coordinate networks are very different to the activations that we use in nearly all of deep learning. And so what's really exciting is actually working out the theory of why. Why does that happen? So the typical workaround for this is to actually revisit classical signal processing. And so like ideas from Shannon and Nyquist, and it turns out that sinusoids are a great activation to use for these types of networks. But they're really susceptible to getting caught in local minima. So Shannon actually showed that if you have a sine and cosine orthobasis with a certain bandwidth, you can equivalently represent them as shifted sinc functions, right? And the width of the sinc function denotes the bandwidth of the signal. So recently, we proposed something called a deep Gaussian network, right? So it's not using ReLUs, it's using Gaussian activations. And Gaussians are great approximations to sinc functions. And what's really nice with these deep Gaussian networks is you get fantastic reconstructions, right? So you get around this sort of implicit bias. And you can actually also apply it to things like NERF. So last year at ECCV 2022, we had a paper called Gaussian Activated Radiance Fields, or GARF. You can kind of see this fun Garfield icon here. So it was an oral at ECCV. And so what was really cool with the work, right, is that if you want to perhaps reconstruct a signal as well as do alignment, so try to do SLAM and reconstructing the field at the same time. And this is a toy example here. GARF has really, really good properties. So I'm not going to get into the details here. There's some other leading state-of-the-art methods. This is our method here. And because of an intervention in architecture, we got really great results and basically state-of-the-art in alignment and radiance field prediction at the same time. And so you can kind of see this firsthand. We can actually solve for pose and the radiance field at the same time, whereas naive NERF sort of fails catastrophically. And as a result, you can get some very nice depth maps and images back out. Another really cool application of this, and something I'm very bullish on, that I think that there's going to be a lot more work coming out on this, is something called physics-informed neural networks, or PINs. Right? So in computer vision, we haven't done much with it. It's huge in physics at the moment. So this paper, and basically the technique is very similar to kind of modeling a coordinate network, but also injecting some knowledge of the outside world. So if I'm trying to model a field, perhaps I'm trying to model fluid flow, I'm trying to model a magnetic field, I know the equations. I know Navier-Stokes. I know Maxwell's equations. I can actually add this into my neural field. And actually, so if I've only got, say, these red dots are denoting where I'm getting readings, but I know the physics of the rest of the field, I can actually recover these things really, really well. And so what's nice, so this paper's got a ton of citations now. It came out in 2019. So it's called pins. It's a really rapidly emerging field. But what's really cool is these activation interventions, like Gaussian, outperform all other architectures for these pins. So another really nice application of this. So to speed up, we've also got optimization. I was speaking about optimization. So one thing that we also notice is with optimization, if you change the architecture, if you go over to Gaussian activations, if you do ReLU, so classical ReLU activations, and this can be transformer networks, CNNs, fully connected networks, it doesn't really matter. You don't see a big difference between, say, using Atom or even a second-order learner. But by changing the architecture, you change the bandwidth of the neural network. And you can all of a sudden start exploring, so something called LBFGS, it's a second-order optimizer. And so you can do much, much faster convergence. So less compute, less data. Another application is in autonomous vehicles. So at the moment, a lot of autonomous vehicles have a LiDAR on top. And one of the problems with LiDAR is very, very sparse. So one way to make it denser is to solve something called scene flow, which essentially tries to get LiDAR sweeps from one frame and connect them to the other frame. And there's this whole paper we had in NeurIPS 2021. But what's cool with it is we propose this technique where we estimate flow as a runtime optimization. So we don't train it on billions of examples. We solve an optimization at runtime. And what we do, we represent the flow as a neural network. And so if you choose the right architecture, you can actually apply an implicit bias. So you solve the flow problem. And so, yeah, we have an example here of neural scene flow. And so you can kind of get examples like this, where you have sparse LiDAR, and you apply it through, and you can densify the LiDAR really nicely by putting those things together. And it actually outperforms all state of the art at the moment. So most of the autonomous vehicle companies in the world at the moment use neural scene flow to actually do that. They don't use a frozen network. They don't do lots of self-supervised learning. They use coordinate networks. One of the drawbacks to it at the moment, but it's really slow. So the green here is our technique, but you've got time on the x-axis and error on the y-axis. So the orange dots are sort of frozen networks that are state-of-the-art. But in ICCV 2023, we actually were able to show that you could do this runtime optimization even faster than a frozen network. All right? So to wrap your head around that, we are solving for the network in real time. We're solving an optimization at real time. It's not happening off, and we get really, really powerful OOD performance. The final thing I'm going to kind of wrap up on is around initialization. So one of the things that we've been playing with a little bit is the idea of thinking about a neural network as an interpolator. So we're used to bilinear interpolation and other things. So let's say I've got a signal with these blue dots, and I want to draw a line that fits a curve between them. I could actually use a neural network to just interpolate between them. And if you use, say, a ReLU network, you can actually look at the initialization. So what we did here is we got a network, and if you randomly initialize, say using He initialization, which is typical in PyTorch, you can actually look at the signal that the coordinate network outputs. So even if the weights are random, the actual signal itself is very smooth, okay? And you can actually do an FFT on it and actually look at the spectrum. And so all the energy is focused in the low frequency. And so then when you train the network, it recovers, it generalizes really, really nicely. So if you look at the reconstruction, you get this nice, smooth reconstruction out. But we thought we'd have some fun. We thought, well, what happens if I had a different initialization? And this is a sort of crazy initialization. What we did is that we created a signal with a high pitch frequency, so something with a really, really high frequency, and then solved the neural network on that high frequency and used that as our initialization. So instead of random initialization, we tried to get the network to reproduce the high frequency pulse. And what we noticed is that it matched the training data. You kind of get this nice peak here, but we get this residual part here. So if you actually look at it, it matches the training data, but it doesn't generalize. Now you guys might be thinking, well, Simon, what's the point of that? It's actually pretty interesting because you can apply this thought experiment to ConvNets. So we actually applied this to CFAR 10. And so what we did is we basically got a neural network and we just did our regular initialization on, say, convmixer. And it gets 100% training accuracy using, say, convnet, ReLU activations. But if you use the regular initialization, you get around about 86%. Exact same architecture, exact same optimization, just the initialization's changed. 49%. Right? So we hear over and over again that generalization is because of the deepness or the architecture. But what we're seeing more and more, it's a balancing act. It's initialization, it's optimization, and it's architecture all at the same time. We've also done a recent result where we've applied this to vision transformer networks. So we have a traditional initialization. And one of the problems with vision transformer networks is they can't work well on small amounts of data. You typically need to train them or pre-train them on a big, big data set and then apply it to the small data set. Now, this is a pain in the butt because you actually can't actively try new architectures. It's really, really slow. So if you ran a VIT with no pre-training, just did random initialization, your test accuracy is around about 60%. But we've been kicking around this idea of structured initialization, okay? And the paper's there's no time to go into it. But what we're able to do is instead of changing the architecture, we can mimic the architecture through initialization. So you can try all sorts of different architectures with very, very little cost. And so this is a new paper that's up in archive, which we're kind of excited by, and requires no pre-training. So, in conclusion, it's an open problem on how architecture, optimization, and initialization relate to data-efficient learning. Okay, so, but you have to consider all three. Most papers lock down two of them and change one, but you can actually swap them out. You can oftentimes get really good results for one architecture, but just changing the optimization or the initialization. So you have to be looking at all three at the same time. A better understanding of coordinate networks will lead to better insights for deep learning in general. I kind of liken coordinate networks to sort of like quantum physics. We're working out places where deep networks, the rules of deep networks break. And by understanding where they break, you get better insights into what makes them work. And finally, and I'm really bullish on this, there's a whole new field developing around coordinate networks and the applications to physics. Not only for doing better measurement, but potentially even uncovering new physics. And this is one thing I'm really excited by. I think there's a lot to do there. And we're just starting to understand how to interleave all these forces. But yeah, thank you so much for your attention and really appreciated this. Thank you.